Today we are going to do section 5.1 on page 478. So first let's figure out what it is. What is a double integral? A double integral is basically integration in two dimensions. And when you integrate in one dimension in calculus 1, we're calculating the area under the curve. So in two dimensions, we're going to calculate the volume under the surface. Okay, so it's exactly the same thing, except that we're going to expand our minds to include two dimensions now. Now in that case, let's look at this picture in your book on page 478, where you have a surface, right? And underneath there's some volume, and your job is to calculate what that might be. Now the way to approach it is exactly the same way, except that we're doing things in two dimensions. We're going to do a double summation where you have the value of f in that area at the bottom, okay? And then you're going to figure out the area, the volume of each, in this case it would be like a stick. Okay, before it was a thin strip and now it's a stick. And you figure out the volume of various points and calculate times the tiny little area down there, where the area is equal to the delta A is equal to delta X, delta Y, right? So you have this rectangular stick thing and you multiply together and then you add it all up, and then that will be an approximation of the area under the surface, as you can see in the following page. There is a picture here. Is easier to see in your book, I'm sure, but you see the thin stick down there, and you do base times length times width times height to find the volume of that stick, and then you're going to add it all up with two summation signs. And then eventually, of course, you're going to let the m and n go to infinity by slicing these sticks to be thinner and thinner, but the same height, okay? Then your approximation of the volume gets better, and eventually you will get somewhere with it. That's the idea. So the definition, let's go to the next page, page 480, where you have the definition of the double integral, which is, as you might imagine, the double integral means you're integrating over an area instead of just a line is equal to the limit where m and n both going to infinity of the double summation. That is, you're going to add one row then of sticks, then the volume of sticks, then you add the next row and the next row and so on until you get it all added up. And then delta A is delta X, delta Y. Okay, that's the definition of it. And so having said that, first you're gonna do one sample, okay, where you make only 4 sticks. That is in the example 5.1, where you cut the region only into 4 areas, okay, so that you don't get worn out counting too many sticks. So your stick is only gonna be in 4 areas, and then you're gonna do this summation, which only has 4 items in it. Okay, so because m and n are only 2 both. So then you're gonna try doing this and see what kind of volume you might come up with, which is just an approximation, of course, because you're only cutting it into 4. That's a very rough approximation, but it's rough but faster. Okay, you don't have to add up like 50 things. So please do example 5.1 as part of your homework to get you a feel for the Riemann sum. I think this thing now is called a double Riemann sum for good reason. And then let's go to next let's go to page 483, where we will look at the property of the double integrals. Now, the properties are almost identical to the property of the single integral. Okay, let's look at them. The properties are all of them except the last one is very intuitively obvious. Okay, for example, if you have the add area of 2 things and two functions, that's the same as calculating the area of one and the volume of one and then the volume of the other, if they're integrated over the same surface. That extends directly for the the single dimension integration. And similarly, a constant can just come in and out of that thing. Okay, and then if you have integrating over 2 areas that has no overlap, all right, then That's what that second condition means. If R is a combination of two separate areas, and then the intersection of the area is empty. Okay, that's what that circle with a line means. That's the empty set, and the empty means there's no intersection. Is what that actually means. So then you can just integrate a function over each area. Well, obviously, right? And then to calculate the volume. And then next, where we have property number 4 is if one function is bigger than another during the whole time, then the integral, that is the volume under the curve, is also going to be bigger. That is again quite obvious. And then property number 5, if a function is completely within a range of two numbers, that is all of the function is bigger than a certain number and then less than some other number, then the integral is also going to be bigger than the volume of that function on the bottom or function on the top. That is a direct extension of the concept of first dimension integration. That is, if you have a curve, right, and then you have a curve and you're calculating the area under the curve. If you have some line that's completely under the curve, then the area under the line under is going to be less than the area under the curve, which is less than the area of the line above the curve. You see, because so these are the three areas. So then the area under the curve is between these two, and the same as if the curve got turned into a surface in 2 dimensions, the principle applies the same way. Now that last property is very useful, but at the same time it's not obvious. Okay, unlike the other properties, this one requires a rigid proof, which we're not going to mention right now because it's going to require something called the Fubini's theorem, which is on the next page, and we're not going to prove that either. We're just going to use it. And while it might not be obvious to prove, it is very easy to use, right? In the sense that if your function, okay, happens to be, you can break it into 2 functions. That is, your f of x, y can be broken up into gx times hy, which it is not saying that. Where is it? It's a product, okay? Well, it doesn't even show it that way, but the point is, f of x, y, you can factor into a function of x times function of y. In that case, then your integration can be neatly broken up, okay, into these things. So everything is nice and clean, so to speak. Well, anyway, so that is the theorem that you're going to use for various problems that is easily breakable. And yeah, notice that the x function will be integrated with dx, okay, in the range of x, and then y function will be integrated with respect to y in the range of y. So that is how it works out nicely, and that is going to, now remember that theorem, because that property, because you're going to need that for doing any homework that you see that is can be easily factored. So having said that, let's go to the next page, and then we have something called a iterated integral. And now in general, here's a very convenient theorem. That is, the double integral, you can calculate it. Well, let's put it this way. There is something called an iterated integral, which just means that you can integrate what's on the inside first, and then integrate what is on the outside. Okay, and how would you integrate what's on the inside? Look at this. The inside in the first line, part A, has dy in it, right? And then you're integrating from c to d. Now in that case, what are you going to do about the x? You're going to do with the x like it's a constant. You just let it sit there, kind of like taking partial derivatives. You just let the thing sit and deal with it later. Okay. Once the integration of the inside is finished, then you have a function that has only x in it because the y went through the integration. And at that point, then you do the second integration, which has x in it. So that is, if you stare at that and envision how that might work out, that is, so for the first integration, x is just a constant, and you integrate it and take carry it along like you do partial derivatives, okay? And when you do partial derivatives, when you take partial with respect to x, y is just a constant that comes along for the ride. So this is the same thing. Now the other option of, the other way of doing, if you're integrating y inside first, then you do that. And if x is inside, doing the x integration first, the principle applies. Then y comes along for the ride. Now that's called the iterate the integral. Now the whole point of this is we don't really care if it's called iterated, because the whole point of this is the most important point, Fubini's theorem, which states that to do the double integral, all you have to do is just do the iterated integral. That is, to calculate some kind of a double thing, all you do is integrate the inside. That is from you do the dy first, holding like the one we just mentioned, holding the other variable as a constant for the integration, and then do the outside integration, where you have just x left, okay? And because of that, you can even flip it around. It doesn't matter which way you do it first, okay? Because they're symmetrical. And it shouldn't matter which way you do it first. So then you can also integrate it from you can either integrate the x first or the y first. And sometimes it might be more convenient to do one first than the other. And you will gain experience of doing that by doing a bunch of homework. And so this is, the Fubini's theorem, of course, has certain requirements. That is, f is a function of two variables that's continuous over a rectangular region, okay? And then the, okay, so it's continuous over some region. I guess that's about all we care about for now, okay? Because, yeah, that's good enough for anybody. It's continuous, period. And also, now the next sentence says that even if it's not continuous, it still works as long as it's not too crazy. If it has a slight break, it's probably okay. You just, everything will work out. But if it has a, yeah, if, well, actually, yeah, see, more generally, it says at the bottom, Fubini's theorem is true if f is bounded on R, and is only discontinuous on a finite number of continuous curves. Well, that is just something that you sort of bear in mind. We don't actually care about it at this point, because we're just gonna use this theorem and apply to functions that normally we don't deal with, things that are too weird. Okay, but just remember that the function does have to be continuous, or at least not too crazy. If it's not continuous, a couple of breaks is probably okay, but it better not go to infinity or anything like that. Or have an infinite number of breaks, so the whole thing is just busted. But we don't deal with that in a basic math class like this, so we're good. So as a result, please do example 5.2, which is applying the Fubini's theorem. What you're going to do in this section is just doing integration, the same integration in Calculus 1, except that you're not going to do it twice, and holding the other variable as a constant for the moment until you do the second integration. Then you can integrate the other variable. So it's a lot like partial derivatives, okay? We're sort of doing the same thing we did before. So please do example 5.2, and then flip to the next page. I'm now on page 486, 5.3, which just illustrates the various properties that we had before. It was such as when you add stuff together, it's the same as adding it separately, that sort of thing. And the same as example 5.4. Please do that as part of your homework. It says property 5, where you have the lower bound and the upper bound. Next, example 5.5 illustrates the property 6, which is the one that where you can factor a function into two parts. If that is the case, then you can just integrate each one. It comes out and probably easier. And then eventually, and so please do that as part of your homework. Next, integrating example 5.6, evaluating the iterated integral. You can, in other words, you can integrate x first or y first. It comes out the same. And so please do that. Example 5.6. Next, 5.7, sort of a similar thing. You're switching the order in integration. Which one should we do first, the x or the y? So please do 5.7. And that's all quite a bit of basic integration that you're doing, but you do practice ignoring the other variable as a constant during the first step of the double integration. And then the next part we're going to look at, so we are now on page 490, where we are looking at the area of the region. Now, the area of the region can be considered as a double integral of 1. Okay, if you calculate 1, then the double integral will give you the area. Which seems to be kind of obvious, but we'll do it anyway, right? That's example 5.8. Please do that as part of your homework. And then example 5.9, you're going to now calculate, after all the stuff we did, we're going to do what we were supposed to do. Calculate the volume under a surface. Okay, so here's a surface, and you will be calculating the volume of it by doing integration 2 times. So that's example 5.9. And the last thing I want to mention is page 492, where there's an area. Now, in Calculus 1, the average, okay, the average in Calculus 1 is defined as the area, the integration divided by the range of integration. Now, the average of 2 variables is exactly the same way. We'll calculate the integration divided by the area. That's the part you're integrating over. And that's and that's the end of this section. We're going to skip the next example because it's somewhat odd and unnecessary, I think. But it's, well, mostly I don't want to do it because there's no integration in it. You're just doing a bunch of I don't know what. Anyway, so let's look at the homework. For homework of this section, please do page 496, problems 11, 15, 17, 21, 23, 27, 29, 33, 35, 40, 47, 49, 51, and 55. And I won't be going over the homework because it's, you're just doing Calculus 1, doing various integration. But it's still good for you to do at least some of these things to get a feel for doing double integration, which is the volume. And that marks the end of this section.